how it works, and we will just do a small just play with the data in MATLAB. So okay, what are the atmospheric radiative transfer models? So these are software computer codes that they model the physical interaction of electromagnetic radiation with the atmosphere, with the molecules, with the aerosols, and so on. So these models are actually used for, well, first to understand how it works, these radiation processes, and then they are having practical applications both in Earth observation and also technological aspects of satellite development. So for mentioning some, we have data processing applications, for example, inversion of atmospheric constituents, gases in the atmosphere, aerosols, and so on. We can also do atmospheric correction of the data. We can use these models to generate synthetic scenes and use it for mission simulators. These atmospheric radiative transfer models, they are also used for atmospheric chemistry and physics, and also they are widely used in climate modeling and weather forecasting. So just to show a few applications, so we have this atmospheric correction, which is the compensation of atmospheric scattering and absorption, and the inversion of surface reflectance. So we remove all these atmospheric effects from the satellite image that is acquired. We can also use it for generate synthetic scenes to imitate what a future mission will be working. So we need to generate this kind of artificial scenes. So with these models, we generate the atmosphere. We can also have applications in terms of atmospheric chemistry, so to derive some trace gases from the atmosphere, for instance, some other atmospheric constituents, and how they react in the atmosphere of the Earth. And also another part is to the study of aerosols and clouds, so to characterize their optical properties, how they influence to the advance of radiance, and how they evolve in time and interact with the other constituents in the atmosphere. So okay, what happens with these radiative transfer models? They are complex tools. So first, they are difficult to use generally. It's a hard entry level. The user manuals are typically hundreds of pages. It's hard to sometimes to understand what is written there and to follow everything. Also, every radiative transfer model works different. So you can learn one, it takes you some time, and then you want to learn how to use another one. And again, you have to start almost from zero. Yeah, and they don't have a common graphical user interface to use for all of these models. So every model have their own graphical user interface. Then a second point is about the consistency of the inputs and outputs. So basically, each RTM is using their own definitions of inputs and their own definitions of outputs. So it lacks some kind of harmonization of this input and output data in terms of format, in terms of content, units, and sometimes even the definition, the way, for example, some angles are defined, it differs from some models to others. Then we have the fact of lack of graphical user interfaces. So typically those codes are working through command line. And yes, there are some graphical user interfaces, but these are customized for specific RTMs. I don't know if there was a question there. I'm sorry. Okay, I will continue. So yeah, so there are lack of common graphical user interfaces for running several or for using several different radiative transfer models. And none of these graphical user interfaces that exist can be directly used to generate large database of these models. So if you want to generate large databases, the fourth point, you need to develop your own scripts to run the simulation, to write the input files and store the data in the format that you want. So of course, you can imagine that if we want to make lookup tables or databases with different models, you have to, again, learn how to do it for the new model. So this, of course, takes time, and it's a complex thing. So, okay, based on that, the idea was to develop this atmospheric lookup table generator, or ALG. So it's a graphical user interface that with that you can simply select your radiative transfer model, and then you can configure the simulations that you want to run. And automatically the software writes the input files, executes the software, the radiative transfer models, and finally stores the output simulations into one single lookup table file for any configuration in the optical domain. So this way you can compare, or you can use different models of the atmosphere in your own and then use the data in your own application. For example, atmospheric correction or stuff like this. So, okay. So in a nutshell, there are main software features here, which are shown by these, let's say, icons. So the first part is, of course, to configure, run, and store the RTM simulations, and then have the data to be used in some analysis later on, in some data processing. Then you also have access through the toolbox to a broad range of public meteorological data and some databases, for example, to define your own aerosols or to define your own atmospheric properties, atmospheric conditions. Then the toolbox is also able to connect with the Aeronet and Wyoming radiosones data. So these are widely used, how to say, the collections of data of ground stations that they measure aerosols and atmospheric conditions. You also can explore the data generated by the RTMs or by the different databases in the toolbox. So you have some options to make some plots and stuff like this to explore the data. And of course, last point is just a minor thing, but it's also quite important, is to have a friendly user manual where you can find all the information about how to use the toolbox and tutorials, some publications and definitions. So you have all the information contained in the same tool. Okay. So currently there are 3 atmospheric radiative transfer models being implemented into the tool. So I started with MODTRAN. MODTRAN is a widely used radiative transfer model. It's based on the DSORT solver, and it models the gas absorption with the K-correlation method. And it covers the entire spectral range from ultraviolet to thermal infrared at a very high spectral resolution of 0.1 centimeter minus 1. Then we also have the 6SV code from Vermote. It's based on a different solver for the radiative transfer equation. Is the single orders of scattering. This solver allows to model also polarization of the signal, but it has some drawbacks. In this case, it has a decoupling of the scattering and absorption, so it simplifies this interaction between the two. And it also covers a much lower spectral range, only between the visible and SWIR, at a lower spectral resolution of 2.5 nanometers. So it's meant mostly for broadband instruments like ALG, SLSTR, Landsat, stuff like this. Then we have another one implemented, which is libRadtran. libRadtran was developed at the University of Munich, and it's in a way similar to MODTRAN. So that means a collection of different functions and programs for the calculation of radiation in the atmosphere in different domains, from, again, ultraviolet to thermal infrared. One of the benefits of libRadtran, as well as 6S as well, is that it's free to use. So you don't have to pay. It's not a commercial software that you have to pay, unlike MODTRAN. The idea that I have for this ALG toolbox is to implement more models of the atmosphere, a little bit to what Jochen has been doing with the ARTMO toolbox, but here with the atmosphere. So I'm currently working with the ARTDECO software. It's from the LOA. It's a laboratory of atmosphere in Lille, in France. Also working with the Python model developed at DLR, the SBDART model, which is developed at University of Bremen, also the SBDART at the University of California, SmartG from a company called iGeos, and ideally as many models as I can use, as we could implement. The idea will be to implement it into the same framework of ALG. Okay, well, I will skip the presentation, then I will show you actually how to use the software. So just to mention a few use cases of these last 5 or 6 years actually using the toolbox. We have been using the toolbox to perform global sensitivity analysis, so trying to understand what is the influence of every input parameter, gases, aerosols, and so on, into the top of atmosphere radiance or in the transmittance of the atmosphere. We have been also using this toolbox to compare different simulations from different atmospheric radiative transfer models. Some application that we have extensively used is to use the lookup tables generated by the tool to create synthetic scenes for the ESA Flex end-to-end mission simulator. So this is the middle image that you can see, for instance. Also, we have been using these lookup tables as well to do the atmospheric correction within the Flex level 2 processing chain. Lately, we have been exploring how to make emulators and statistical regression models. So the lookup tables that we are generating with the tool are used for training those models. And there is always a part of teaching at master and PhD level. So like the tool was developed mostly by myself while I was working at University of Valencia and also at now currently Magellan. But I'm collaborating, of course, with Jorge Vicent Servera at University of Valencia and interfacing with, as possible, ALG with Toolbox ARTMO. But yeah, there are many other collaborators at different institutes, as FMI, in Mexico as well, at University of Valencia, working with satellite data processing, but also with machine learning. So just the last slide, if you want to know more about the toolbox, you can go to the website of artmotoolbox.com, and then you can register there, and then you will be able to download the software. It's free to use. If you want to contact me, you have this contact information here, so you can write to my email address or to the email address of the ARTMO Toolbox, or contact me through ResearchGate or LinkedIn if you want. And eventually, if you want to know a little bit more details of the toolbox, there is a publication here. And if you use the toolbox, of course, I will ask you to please to refer to this publication. So I think then I can move to show you a little bit how the software works. Okay, first, okay, let me check first the website. Okay, so this is the ARTMO website, and once you have to register, and once you register, you can come here. Here on the website of ARTMO, you can find information about the atmospheric radiative transfer models that they are currently implemented. So you can read more information about this model, for instance, MODTRAN, and you can see more information and some publications here. Then you have information about the ALG directly on the toolbox on the website of ARTMO here as well. And then, of course, the most interesting one is to download. So you come to the download part of the website, and you can actually download directly here. You will download a zip file, and you have a short installation guide. Basically, within the zip file, you will have all the package, including the executable file. For running the executable, you will need to download the MATLAB runtime compiler for the version 9.9, sorry, so the 2020B. And then you will be able to run it in your Windows environment without needing having MATLAB installed. So it's a standalone application. Also, ALG can use all the ARTMO toolboxes that Jochen presented. So in particular, if I come here, you can use for automatic scene generator. So you can generate some scene also using ALG. You can use the emulator toolbox to create emulators of atmospheric data. You can do the combination of radiative transfer model from canopy and bring it up to top of atmosphere. And I think that's mostly all. So, okay, once I gave you this brief introduction on how to get this, then I can show you how it works. So hopefully everything will work well. Let me check here again. Okay, so first you have the toolbox here, and basically you will have several buttons where you will find information. One of them is the help button. When you press here, and you will find different icons on the website, you will have access to the Toolbox help system, which is a web-based system. And here you will have all the information you need. You need to have information about the third-party software radiative transfer models implemented, so you can read more information about MODTRAN 6, some information about how to install the software, for instance, with all the information that you need step by step. You have information about the different variables that are actually implemented in MODTRAN. You can click on them, have all the information, all the references at the bottom. And here you will have it for all the atmospheric radiative transfer models implemented. You of course have step-by-step procedure of how to use the software, and you can just go here, and what I'm going to show you next, you have all the information written here. You can also have some part of tutorials where you can have you can learn how to use the toolbox with some like examples of applications, let's say. So okay, let's see. Okay, the first thing that you have to do first is go into settings, and in settings you will be able to edit your software. So basically, it's the first thing you have to do. For example, I select the toolbox, the possible models that I have. So MODTRAN 6, for instance, you have to select where you have the executable file, and with that, basically, you are done. Once you are done, you click apply. It saves the data into an auxiliary XML file where it stores all the information here. And then once you are done with that, you can already start running simulations. So you go to the first button here, run simulations, and you will start, you have different tabs with different steps that you have to follow, let's say, in order. So first you will have to select which will be the lookup table file. So the path to your lookup table file. So, okay, test. Here you can select running different parallel executions. So if you have several CPUs in your computer, you can actually run several runs in parallel to save some time. So, okay, I will check too. You will select what kind of user you are, basic to advanced. It means you will have access to more or less parameters of the toolbox. So, okay, I will select the model that I want to use. For example, here, I want to use MODTRAN 6. You can have access, as you see, to all the models that they are currently implemented. So MODTRAN 6. Then you have here operation mode. It's about how the radiative transfer model is used. So the radiative transfer model can be used typically in 3 operation modes. The transmittance, basically, you will get the spectrum of gas transmittance for every constituent of the atmosphere. So the spectrum of oxygen transmittance, water vapor transmittance, ozone transmittance, and so on. You can have another mode in which you will be able to simulate the radiance acquired by a sensor at top of atmosphere. Here we use external databases of reflectance, and so it's not yet connected with ARTMO. And the typical one that I mostly use is the transfer function. So the transfer functions basically allows you to have your atmosphere decomposed in different terms. So the path radiance, so it's the reflected radiance, the radiance that is intrinsically reflected by the atmosphere, but you will have also information about the transmittance, direct or diffuse, that is transmitted from the sun to the ground and then from the ground to the observer, plus the spherical albedo. So you will have all these things here. So the transfer functions is actually very useful if you want to make synthetic scene generation or if you want to make atmospheric correction. So this is one that I use the most. Then you can select how to distribute samples in your input space. So, okay, if I go to advanced, you will see more options. The typical one is the manual gridded sampling. So basically, you will have let's say 2 variables, and then you want to put 3 values of the first variable and 6 values on the second variable. So you all the combinations of all the possible combination of these variables, but you have also pseudo-random filling of the input space. So the lighting hypercube is the classical one that we are using, but there are others like the Sobol or the Halton, and there are some other implementations. I'm not going to go into details here for the moment. But okay, let's go for the easy one. It's manual gridded sampling. By the way, if you want to go to find some more information, you will just click here, and this will direct you to the part that is interesting for you. So here you will have all the information about the sampling and so on. Okay, the other conditions or the other inputs are not necessary for this particularly sampling strategy and operation mode. So then we can move forward to the input variables. So here we have divided the input variables in three main categories: atmospheric, aerosols, and geometric, which is our clearly identified. Okay, I think there's a problem here. Sometimes the toolbox doesn't load the entire. Yeah, here it forgets to show the table. Sorry, so you can just normally refresh again. Sorry for this small problem here. Okay, now you can see the table. So okay, let's say we want to take two different models. I don't know, mid-latitude summer and mid-latitude winter. So then we will add it on the table. We also want to modify the water vapor between, I don't know, between 2 and 4, and we want to put 3 samples. So you can see these samples, how they are distributed here. This is linearly distribution, but you can have other distribution. For example, here, so you can have different distributions of your data, and you will find the data here. If you say, okay, I'm not happy with this number, I want to put a different one, okay, 2.6, so you can edit and you can modify and add more values on your lookup table if you want. Then you will select aerosol models, for example. So you have different models here in MODTRAN. You have the typical one, rural, maritime, and you have other options. The toolbox is also connects with the OPAC database, so automatically OPAC is run, and the the optical properties of aerosols are loaded, and they are then inserted into MODTRAN. Let's say we want to have just 2 aerosols. And here as well, you have information about the geometric conditions. So you can, for example, modify the solar zenith angle or the ground altitude. If you are working with airborne data, you can also modify the sensor altitude as well, and all the kind of information. If you are not editing, you don't need to edit all the values actually. So if you are not editing them, ALG will use default values. And these default values, they are actually, you can access to them in settings and modify what will be these default values. Okay, so I'm happy with the input values that we are going to use. So in this case, we are going to generate a gridded sampling database. So that means we are going to do all the combinations here for all these possible variables. So here on the spectral configuration, you can select the configuration of your instrument, let's say, or the spectral range that you want to simulate, and also the spectral resolution that your model, in this case MODTRAN, allows you to select. You have some predefined configurations from different sensors. One comment here is that the spectral resolution is always, let's say, high spectral resolution. So if you would like to use the data for a specific sensor, you will have to make the spectral convolution on your own scripts later on. This way you can take into account, for example, a smile effect on the instruments, or use the same lookup table for different instruments eventually. So let's just leave it the default here. Well, one thing is that you can also edit different spectral bands. So for example, I want to simulate between 400 to 700, and then suddenly from 1000 to, I don't know, 1200. For example, and we can use different spectral resolution for the simulations. The surface tab is, in this case, not activated because we are only simulated transfer functions, not top of atmosphere radians. So then we can move forward to the advanced configuration. So this is some advanced configuration for the radiative transfer model. So for that, you need a little bit to know what you are doing. So for this, it's important also to obviously read the user manual of ALG or the user manual of the radiative transfer model that you are using. By default, these options will be preset, so you don't need to worry too much about it if you are not an expert of these things. So once we finish, we just run the simulations. It asks for confirmation. All the information will be stored in an XML file so that you know the configuration that you are going to use for your lookup table. As we are happy with that, then, okay, so you saw the bar, ALG was writing the input files, and now automatically through a BAT file, so a script is basically running MODTRAN in this case. Just to show you how it is here, how it looks. So we basically generated this loop test. So we have the XML file of the configuration that we have. So we basically have all this kind of information about general configuration of the software, of the simulation, and then the parameters configuration divided by blocks. So the atmosphere block, the aerosol block, or the geometric block. The geometric block in this case is empty. We didn't add any value that is not the default value. And here you have all the combinations and also the configuration of the spectral simulation. So ALG is also doing basically this, what it is here, this BAT file, which is basically a simple thing. It tells you, okay, my lookup table file will be in this folder here where I selected. And basically I have an execution of MODTRAN with the given input file. So MODTRAN understands this. Basically what we are doing is running MODTRAN here. And therefore we will have what happens here. So we have this loop test _1 for the one CPU. If we will have several CPUs at the same time, we will have different folders. And on the tape folder, you have information about, well, you have all the inputs. For example, just taking one. So this is an input file for MODTRAN. ALG automatically writes these input files. So for example, you can use ALG if you want to do another simulation, but you are some very specific simulation. You can use ALG to define a preliminary, let's say, file, and then you can edit it by hand and run your own simulation, for example. So this is something that you can actually do. What else we have here? Yeah, well, in this case, it's more MODTRAN. MODTRAN is generating these output files, the so-called tape 7 files. And here you have all the information about those, let's say, transfer functions, the total transmittance, the thermal emission, the multiple scattering, the single scattering, ground reflected radiance, the frequency or wavelength. So you will have all this information here. What ALG will do basically is taking those files, reading them, making some calculations with them, and then store the final data onto a HDFI file. So, okay, here we are with, let me check because I maybe put my simulation. Okay, it's 32 simulations. We are almost finishing. Yeah, so now it's the last one. So let's see. Okay, so now while it was executing this MODTRAN, you could actually close ALG. You don't need to have it activated. You can actually close safely, and you have to wait until the simulation has finished. So now you can see that it's not running anymore. You can press enter. You can see that your simulation has finished. So you can now safely close this window. Okay, but then you don't yet have the lookup table. So what we will do is to package those simulations into the lookup table file. So we press the second button, package load, and then we have to select the lookup table that we wanted to generate. This was the lookup table test. So when I click OK, it will read the output files, those tape 7 files in the case of MODTRAN, and it was storing the information into the lookup table test H5 file. So this will be your lookup table that you want to use later on. You can also use ALG here if you want to generate new atmospheres, for example. So here you can go and read data from the CAMS or ECMWF need real-time data, or the NOAA reanalysis data as well. So this is data that is stored automatically. So for example, here I will select, I don't know, I will select another year maybe. Okay, and then I don't know, 0.3, and then the latitude 35. Okay, hopefully it works. Yes, exactly, it works. So it read the data and it stores the atmospheric profiles here for all the gases based on this particular data. You can change the units here if you want. You can edit the atmosphere by hand if you want, or you can fill by some default atmosphere. The typical ones are tropical, mid-latitude, summer, winter, and subarctic atmospheres. You can plot here the data that you have saved, for example, here, and you can see the temperature profile, or you can see the ozone profile, and you can see how the different atmospheres, they differ on their vertical distribution. And all these atmospheres, they are actually stored in an auxiliary file within the folders of ALG, and you can use these atmospheres to insert them in your radiative transfer model. So this is done automatically. So you have different sources of these atmospheric profiles. And the same thing, you will have it for the aerosols. So you can define new aerosols for your MODTRAN simulation, and you can say, okay, I want an aerosol based on OPAC, and you make here the combination. So, okay, 50%, 50%, for example, choosing the relative humidity that you want. Then you select your name, and then you save it, and you will have in a database for using it later when you want to run your simulations. If you want to have a specific aerosol, I don't know, maybe you are having a field campaign in which you are flying an airborne instrument, and you say, okay, I really know what my aerosols are. I know really well what my atmosphere is. So you can use this information to do your simulation that you need for this specific field campaign. You can have another access to data is the Aeronet and radiosondes. So here, okay, basically it connects through the websites of Aeronet and the website of Wyoming radiosondes. When it's finished reading, basically you will have all the stations. So this is the same, if you're familiar with Aeronet, this is the same as going to the website of Aeronet and clicking on the station that you want. So for example, I can come here to Spain and I can select a ROI. So, okay, I want to download all the Aeronet stations from this area. So they are selected as points here. Plus, I want to select this one here. So you can select it by one single point. You can select the dates that you want to download. So let's say from the 1st of June until Friday 4th. And then you will click download. And this will tell you, okay, I will download the data somewhere here. So for example, here, okay. And then test. Oh, sorry for that. Okay. So it will download automatically, connecting to the website of Aeronet and download all the data that you have. And then the data will be available here. Oh, well, in this case, okay, that's something that happens. Sometimes you select some dates, but for these particular days, Aeronet doesn't have data. So of course, nothing is downloaded. So you have to check exactly what you want to download and everything. You can also make the plots of this Aeronet data when you download it, of course. And also for the Wyoming aerosol, well, Wyoming radiosondes, you have the same stuff. You have here all the dots are all the stations of Wyoming where you can have radiosondes data that you can download. And these radiosondes and this Aeronet data, you can also use it for generate your own atmosphere. Okay, so this is regarding how to use the toolbox. Pretty fast and general overview. We have prepared a small tutorial here to use the data. Okay, so basically what we will do is we will see what is the data that we generated for a lookup table file. We will do simulations of top of atmosphere radiance, and we will see the impact of different atmospheric properties. And then we will see how to use it if we want to simulate our own sensor. So, okay, so the lookup table here that I made, it was based on MODTRAN 6 again. with this input configuration. So it's 400 to 2500 at very coarse resolution, with 2 models of atmosphere, mid-latitude summer and mid-latitude winter, 3 aerosol models, rural, maritime, and urban, with different contents of water vapor and different values of aerosol optical thickness, as well as solar zenith angle. And then the other variables are fixed to the default values, which is mainly nadir view, ground altitude at 0 kilometers, sensor at sensor level, at the satellite level, and so on. So let's see what we have here. Okay, let's show first the content of this file. So the netcdf file, the HDFI file, which is the lookup table file, has all these, has some attributes, some different data sets where you have information about, for example, the solar irradiance and the units with the attributes, some the output data from the model, the header information. So what is the input variables that you choose, the wavelengths, and so on. This file, let's say it's well, it's not complex, but okay, it's not so straightforward to use. So in ALG, we have also developed some toolbox or some functions to use the data in Matlab. And we are also working now to develop these functions also for Python. So eventually you could implement or use the lookup tables also in Python. Anyway, the data is HDF5, so you can have your own scripts to work with the data. Okay, so what happens when we read the data here? We have different information, which is shown in this Matlab structure, like the radiative transfer model that you use, the variables that you use, the wavelengths, the solar zenith angle, solar irradiance, and so on. You can see, for example, here the solar irradiance plot, or you can also see the distribution of points, for example, in this particular data set of aerosol and solar zenith angle. This was also gridded sampling. Okay, the lookup table has in total 1,400 spectral channels for 6 outputs, so the 6 transfer functions, and for nearly 1,000 combinations. So these 6 outputs are those here: the path radiance, the diffuse irradiance, the direct irradiance, spherical albedo, and the direct and diffuse transmittance. And you can see here the plots of these variables. So these are the ones that you will be using for doing your own simulations. Then okay, we can also do a synthetic simulation of top of atmosphere radiance. So basically here we are reading a Lambertian reflectance from a vegetation target, and then we will combine it to generate the top of atmosphere radiance. So, okay, so basically, okay, we have this is the reflectance that we want to use. Then we will select the atmospheric conditions. Okay, in this particular case, I'm selecting just the mid-latitude summer, maritime aerosols, water vapor at 2.5 grams per square centimeter, given aerosol of 0.3023, solar zenith angle of 20. So basically here you have the top of atmosphere reflectance for this specific condition. And then we can change the configuration for a lower water vapor value. So you will have here the information or the effect of having a lower aerosol value. Here in yellow, you have less water vapor, so you will have less absorptions. Or we can also have, for example, higher aerosols. So here you have the impact of the aerosols, particularly in the blue, you see that you will have more scattering from the aerosols. So you will have more bluish color corresponding with the previous simulation. Okay, so that's basically it when simulating top of atmosphere radiance. And then you can also make use of some toolboxes inside of ALG, some functions inside of ALG. For example, this convolve ISRF makes the spectral convolution of the high resolution spectrum here to a lower resolution spectral range. In this particular case, I'm going to simulate a kind of CHIME instrument, hyperspectral instrument mission for 10 nanometers of spectral sampling and also 10 nanometer spectral resolution. And you basically have here the plot at high spectral resolution, let's say from MODTRAN, And in the circles, you also have the plot for the resolution of kind. So with this, I think the tutorial is finished. I think I'm still, maybe I was a bit long, but there is still 15 minutes for questions. So if you have questions, yeah, I can